Okay. Hello, everyone. I'm Ujjawal. I'm here to present on the topic of covariance fluxes of pesticides in atmosphere. As you might know, agriculture contributes to feeding around 8 billion people in the world, and plant protection products plays a substantial role in catering this industry. Earlier in the time, there used to be natural products, but as the industry has evolved, so is the complexity of the pesticides that are being used widely. But given the physicochemical properties of the pesticides and given the methods that how they are applied in atmosphere, they're bound to leach in the atmosphere in not the most expected places. So we need to understand how they evolve and how they leach into different parts of the atmosphere. Okay, sorry. So as during the application, the first part is through seed abrasion, where pesticides that are coated with different insecticides break down and can go in atmosphere, and directly through direct surface spray drift fertilization through plants or through directly soil during the application. The next one is through photochemical degradation and in the presence of different radicals that are present in the atmosphere, where pesticides can convert into different byproducts, can act as a sink, but can also convert into products that can lead to decrease in the ozone, increase in the ozone concentration. And the next one is through long range transport, where pesticides have been detected in the most unexpected places like Antarctica as well, where they are being trapped as a sink in different places, which we don't where we don't want them to be. So we need to understand and quantify how the pesticides are going in atmosphere. So what I'm trying to do is I'm trying to quantify this exchange from biosphere to atmosphere for these pesticides. How we can do that? Sorry, just one thing before that. There are some regulations in place to tackle all the changes in the pesticides in atmosphere. The first one is basically around the vapor pressure concentration of pesticides, which says if uh, the vapor pressure of the pesticides that is there in the active compound is greater than 10 to power minus 4 and 10 to power 5 Pascal, it should be there should be a thorough assessment done on their potential to spray to do a short range transport. Recently, there's a UK wide national action plan for pesticides, which is trying to reduce the concentration and the effect of pesticides by 2030. So they have given some pesticide load indicator which they are trying to minimize, and all the load indicators they have been using are basically around soil and water parameters, which basically constrain whether they are going in soil and water. So there's a bit of a regulatory gap in the area where all the assessments have been done on pre-market products, which creates a potential gap between the real-time assessments and the ideal conditions. So what I'm trying to do is I'm trying to understand, as I said, the evolution and how they go in atmosphere. How it can be done is by combining a chemical ionization mass spectrometer with a sonic anemometer. How it is going to help us in understanding these pesticides in atmosphere. So imagine you are having your sonic anemometer in a field which measures vertical wind speed into different vectors, and your mass spectrometer down in a trailer. So as wind blows in, there are circular eddies formed in the atmosphere, which is basically turbulence that is created in the atmosphere. And it is being detected into three different vectors by sonic anemometer, which is the vertical vector of the wind speed and two horizontal vectors. And as the pesticides, then in the influence of these turbulence, advect past our sensor, and we record that simultaneously in our sonic anemometer and our mass spectrometer. And we take whatever value is from higher from the average value, we combine that, and that's when we get eddy covariance fluxes, which is essentially what I'm trying to get out of these pesticides. Uh, yeah, and basically it shows you you are limited by how much fetch of an area you have given the height of your tower. So before we go into a field measuring pesticides, we need to optimize a mass spectrometer, because our mass spectrometer, how it works is you've got an iodide signal which binds with a molecule, and that's how you get your compound detected in your mass spectrometer. But what it also does is it also combines with water that is present in the atmosphere, which has varying concentration, and that induces extra sensitivity in our instrument, which we don't want, because that would induce fluctuations in our fluxes, which might not be natural, which might not be coming from the water vapor, which we don't want. So we added a dopant into our system, which is acetonitrile. So what it does is it quenches all the effect of water that is there in your system, and so you have basically nullifies all the water vapor effect. So that is what we want in terms of consistency of our instruments measurement. So we did a basic study in the lab just to see if the acetonitrile thing is working well or not. So when you see the blue line in the plot, which is without acetonitrile, without the dopant, as the humidity is increasing, you're seeing a twofold increase in your signal value. And in the orange dots you can see in the plot, this is the one that is with the dopant. So your signal with the humidity is changing, but not to the extent that we would want to discard it. So we have optimized our instrument now. So now the next thing is to find a measurement site. Luckily, we found a measurement site in Rothamsted Research in Oakhampton, down in Devon, where we did our sampling not long ago. We just finished it 2 weeks ago. So we started from 20th March till 14th-ish April, and we did continuous real-time sampling and in the close proximity of agricultural environment where regular farming practices were being taken place. And this is the mark location is our measurement site, which is right next to all the agricultural farms. So this is a basic schematic of what our instruments and everything we're trying to do looks like. I'm going to talk about it in the next slide. So this is the schematic. So in the image towards your left, you can see the sonic anemometer at the top and a U-bend where, which is our inlet, which is insulated. So to avoid any so to avoid any stickiness into the instrument. And on towards your right, you can see the trailer where we have kept our mass spectrometer, and our inlet is going down in the trailer. So this is what it looks like from inside. So we've got a 3.6 meters long inlet, and we've got a 35 second liters per minute of flow rate. So why we have such a high flow rate is because we want to have minimum residence time in the inlet, because our measurements are happening at a separate gap, because sonic anemometer is measuring at 3.6 meters and our instrument is sitting down. And we try to maintain a turbulent flow because you need a plug flow profile, because that way you can ensure there's even mixing happening in your lines. And obviously the lines are heated just to avoid any sticky compounds, and so that you can have even flow. Uh, Before we get any results, there are certain steps that we need to take into consideration. So the first one is for your mass spectrometer, you need to do mass calibrations, you need to do peak fitting, you need to do peak identification. These are the major ones, but there are some more steps. But I've highlighted all the major ones now here. Given your data, you have extracted the molecular composition of your data, and you're going to combine it with the wind data, and you're going to put it in EdiPro software, which basically calculates all your fluxes. In that, you do tilt correction, which basically takes care of all the alignment of your sonic anemometer, and you do averaging of 30 minutes for calculation of your covariance. You do lag time composition because you've got a gap in your measurements, so you need to compensate for the lag time that is happening in your measurements. And you need to do spectral analysis, which I'm going to talk about in later slides. So this is a general profile of how our weather was looking like. So we've got a maximum wind speed of 6 meters per second and a maximum temperature of 15 degrees, which was dropping down to 4 degrees in the night. Uh, so now is the interesting part. In the first image, you can see these are all stability parameters, which shows us how the turbulence is creating in the atmosphere, which we need to know first before we delve into later parts of the data analysis. So in the first image, you can see the dropping values in the afternoon, which is a Munin-Obnikov length. So what it tells us is that if the values are dropping, you are having buoyancy flux, which tells you that the atmosphere is not stagnant. There are some turbulences that is continuously happening in the atmosphere. In the second figure, you can see the peaks happening every time in the noon, which is basically friction velocity, which is another parameter of saying that you've got good turbulence. There's no stratification, which is what we want for eddy covariance calculations. So we did a footprint analysis just to understand how our fetch is looking like, which areas we are covering, and which all directions we were. So given the height of our instrument, we were sampling from around 3.68 meters. So we have got a fetch of around 400 meters, which agrees with the literature value on each side. And it helps you understand where your your contributions are majorly coming from, and if in case you need to correct for some uh, diversions and all, you can do it given with the help of this uh, footprint. So the first thing we got from our analysis is the momentum flux, which tells you how the shift has been happening from atmosphere to the surface. So you can see the drops in the signal during the afternoon in every day. So I've just taken a short period of time because it was too much of a data analysis to be done for this time period. So I've just taken 7 days where I know consistent weather was there and there was no interruption in our measurements. So I've just taken 7 days here from April 1st to April 6th. And you can see the decrease in the momentum flux, which basically tells you that the momentum has been transferred from up in atmosphere towards your surface, which tells you that there is continuous exchange of energy happening in the atmosphere. The second one is your sensible heat flux, which basically tells you whether you have got good measurements, whether you've got a heat exchange happening from the atmosphere. So these are all the parameters that ensures that okay, you've got a good measurement side. There's no obstruction. You can see all the basic atmospheric fluctuations that you should be seeing. Yep. So not this one. First this one, yes. So given the time we were there at the site, we were hoping that we would see some pesticide application and we would be able to calculate some good fluxes, but we were not so fortunate. There was no pesticide application happening at that time. But it is not a thing that we need to worry about now, because first we need to target is to get a working eddy covariance flux system. So what we try to do is we try to get fluxes from nitric acid, which we know is having a deposition flux. So this is a diurnal profile of nitric acid. You can see the drops happening consistently throughout the afternoon, which is what we expect for nitric acid. And we try to get some flux out of it. And this is what it looks like. It is not really a great result in terms of the fluxes. There's a huge variations happening before and after each period, which is not what we expect. We are seeing some deposition happening in certain parts. For example, if you'll see in April 3rd, you are seeing drops in the values of the fluxes, which says basically there's deposition happening, but it is not consistent throughout the results, which shows that there's a bit of a gap, there's a bit of lag in your data analysis. It might be induced by stickiness of your compound. There are several parameters that we need to take care before we make any conclusions. Uh, just to highlight here, this is a power spectra which basically breaks. So we were recording at 10 hertz, so which is a high frequency. So we need to break different frequencies into different intervals so that we know what contribution is coming from what frequency. So you can see all the blue lines that are going down. These are different components of wind, W, V, and U, which basically tells you that it's in log scale. Just to tell you that the decreasing values are showing that the contribution of uh, uh, low frequencies are being transferred to high frequencies. This is what we want to see, and this is what it is showing us. But the black line you see, it is the frequency response of our chemical ionization mass spectrometer, which is not really great. It is showing there's a lot of white noise coming into our instrument. We would not expect it to look like this, but this is what we have for now. Uh, and we did a covariance power spectra as well, which basically aligns your contribution from two parameters simultaneously and gives you the frequency distribution. So it is consistent with the results that we have seen for the wind parameters and your sensible heat flux. So the yellow line that you're seeing is sensible heat flux, which is taken as a standard, uh, and it can be compared from for other species that you're trying to measure, because the sensible heat flux is gonna remain constant because it is not deviated from, it has not got any other atmospheric or instrumental influence. So you can see it is following well with what we're going to expect in our literature value. But the black dots you're seeing is scattered throughout, which says that there's a bit of a lag in capturing the covariance of your nitric acid flux, which is not really a great thing. But this is just a disclaimer that it is in a very early stage of the measurement. So there are some things that we need to take care first before we make any conclusions. So this is just, so I don't have any conclusions for now. This is a summary and more of like a takeaway from what we can do in the later parts of our study. So as we can see, we've got some developed eddy covariance system. we've got some good fetch in the area we were doing measurements, but there are certain parameters, like we need to do some high frequency corrections. We need to test different corrections in our instrument. We need to take in account for different frequency changes happening in our instrument. And we need to take some different periods as well, so that we can understand whether the variations in the fluxes are just can be understood if we take a longer averaging period of the time. Uh, that's all I have now. Thank you very much, and I'm happy to answer any of your questions.
Thank you very much. Ujjawal, do we have any questions? Tom?
Thanks for your talk. So you said there's no spraying during your field campaign. So the chemicals you're measuring coming off, are they from last time it was sprayed, or are they naturally occurring?
No, so the nitric acid we were seeing was from natural occurrences. There was no uh, uh, emissions coming from the spray that happened. We could see some traces of pesticide byproducts, but it was not conclusive enough to get some eddy covariance flux out of it.
So then you're measuring how the airflow should assume that you get similar results if you had spraying. You get similar
Yes,
outcomes.
yes, 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 yes.
You didn't by any chance see any sulfuric acid during the day, did you? Because nitric acid can be a little funky with compensation with ammonia and humidity dependence and all sorts of stuff. Whereas sulfuric acid, you should be able to get a deposition velocity from your physical meteorology data, and then it's just unit uptake.
Yes, we didn't look at that because we were uh, pretty focused on nitric acid at that time, because we thought we might get something out of it. But there's, yes, obviously still a lot of things that we need to look for. There are, for example, we found different organic acids as well that we could see and get some good enough deposition fluxes out of them. But it was still in some early stage. But yeah, obviously I would love to look at that as well. But yeah, this is what we have now.
Final questions? Down here, Francois.
Thank you. I wanted to know if there's some averaging effect in the sampling line you use to. I wanted to know if there's some averaging effect in the sampling line you use to measure the fluctuation of concentration.
Sorry, I didn't quite follow what you said.
Yeah, you use a 3.6 meters sampling line.
We use 35 second liters per minute, yes.
Is there some concentration averaging effect in the sampling line? Because you need to know the measurement of high frequency of your concentration.
Sorry, I didn't understand.
So I think the question is, you've got this high sampling velocity, but
Yes.
can you be sure there's no that your sampling frequency is not compromised by the sampling line?
Oh, okay. Yes, sorry. I get it. Yes. So the first thing that we need to take care of is having high flow rate, which tries to minimize your lag time. So we calculated that it was around 1.2 seconds, and we did a covariance maximization, which basically does find whatever gap is there in your covariance spectrum, which was also aligning well with what we see in that spectrum, and we compensated for that. So ideally, in ideal situation, we would not want, we tried to remove all of that effect, but if it is there, we need to analyze it further down the road. Is that what you? Okay, thank you.
Thank you very much, Ujjawal.